So that's what we use here in this nation.
So in the US, we use 120 volts. That's like the standard. But why 240? Yes, we can have 240 volts in our house. Do any of you guys actually plug devices into 240 volt outlets? Not consistently. You might have high power applications plugged in, like your dryer, or maybe a table saw or something like that if you have a wood shop. Your oven might be 240 volts because of, again, high power needs. But basically in our house, you've got 120 volt outlets, and that's what you got. So why 240? Why is that the upper end? Why can we do 120 to 240 volts? And the answer is rest of the world. The rest of the world. Most of the other world, if you're not 120 volt, you're up in the 240 volt range. And that's the standard coming out of freaking plug in your house. So by doing that 120 to 240 range, it's a universal power supply. So you can actually take your cell phone charger, get one of those really cheap plug adapters that takes it from the US style plug to the European style plug, and plug your cell phone charger in there, and it will work. It's not going to destroy your cell phone charger. So it makes it very universal. You will also notice, if you ever actually look at it, it normally says 50 to 60 hertz. And again, here in the US, we normally use 60 hertz. Over in Europe, you're normally using 50. So that's why it's 50 to 60 hertz. So, and it is actually wonderful to have universal devices like this. I am taking advantage of that in my closet in my front of my foyer. There's a little, I just repainted it, redid the inside of it, and there was an electrical junction box at the top. I'm like, oh, cool, I can get 120 volt power in here so we can like charge batteries and vacuum and things like that. And I was like, okay, honey, watch the voltmeter. I'm going to flip breakers. Tell me when the power goes off. I flipped every 120 volt breaker in my house. The power didn't go off. That's not right. I'm looking at it. Okay. My wife actually, like, is it higher? Like, does it power the heaters or something? I'm like, it shouldn't. But so I went and started flipping the 240 volt breakers. That turned it off. That was a junction box, and it controls the heater for the foyer, which I don't even know where it is. It's either in the floor or in the ceiling. Not sure which one. And the heater in the bathroom. So there was just a junction box purely so they could splice wires together there. Like, okay. And I'm like, you know what? I'm still doing it. I just put freaking 120 volt outlets on there because of things like the vacuum cleaner. I read the back. It said 120 to 240 volts. So I put the wrong style plug on it, which is probably not the code, but that's fine for me. I wrote on the faceplate, like, warning, 240 volts only, you know, like trying to like make people not plug this, like the vacuum, like an actual vacuum in. But my little cordless vacuum that we use to, you know, clean up after my kids charges fine off of it. So I put a big warning on it. So, like, you know, you can plug a cell phone charger in there. You know, most things that if it's an AC to DC can get plugged in there without any problems. So anyway, but that's why it's 120 to 240 volts. It's a very universal supply. But anyway, so I believe this is our input power. This is our relays, or not our inputs for the PLC. So they are expecting DC voltage of the 24 volt variety. And then relays is our output. So we have our power in, our input, and our output. So I think that's why this is an AC/DC relay. Alan Bradley doesn't do this type of crazy naming scheme. They do some other crazy naming scheme. It's the, like, 1769. I'm like, you gotta forget me. So when you're looking at these things up, it is important to make sure that you actually do, you know, look up all these crazy ass things. In fact, if I pull up the Micro 800 series, this is the 2080-UM004D-EN-E. That's what, that's what the top of this thing is labeled as. And here's the catalog numbers for everything. I mean, it's like, this is the Micro 800, yet all of them start with 2080. Why? I got no clue. Okay. I digress. So, PLCs are, overall, in my opinion, wonderful devices. Let me just move this up. Can't go any higher. That's interesting. As I talked to you guys last class, in previous days, if you wanted to hook up, say, 3 limit switches to a relay or whatever, you would do a limit switch to a limit switch to a limit switch, to your relay or whatever output it was. And you would physically take a jumper wire to all those things. Fine and good. No real issues there. And when you're first wiring your machine up, it's not a big deal because you're running all the wires anyway. So where you run the wires to doesn't make any difference. The problem is down the line when you want to say, you know what, we really don't need this limit switch anymore. So now you have to go take that limit switch, unscrew it, connect the two wires together there, which makes a joint there that you might not want. And, it's okay. And then you're like, oh crap, we need to add another one over here. So now you got to break a wire to come up and put another limit switch in and, then come back down. And life just gets very, very, very annoying as you're constantly tweaking this wiring diagram. And more importantly, hopefully you're not just tweaking it on the machine. Hopefully you're tweaking the actual diagram that shows you how everything's wired. And hopefully you're updating the numbers. So hopefully this is wire 1, this is wire 2, this is still wire 2, and then 3 and 3, and 4 now comes up to here, 4, 5 to 5. Hopefully you're updating the numbering as well. And that's how you did it before PLCs. And let me tell you, when you had stupid numbers of these types of things that all had to start at the same time. You would have something like this. Pull it up, open the image in a new tab. There we go. So here's your standard push button start. All right, and as you can see here, this button now, you've got a little bit of a dividing line. You've got a red side and a blue side. And the red side, I'm going to guess, is your normally closed. And the blue side would be your normally open contacts. So depending on how you got push button need to be wired, you would wire it differently. And if you had 10 things that all needed normally open contacts, but they couldn't be in the same circuit, you would take these blue and red section and you would just stack them. So you would have another thing here like that, and then another one there like that, another one there like that, and you would just keep going with it. And every time you would add another one of those, it would actually make the button harder to press because all of those have springs in them. So technically, there's no limit to how many of these things you could stack other than the depth of your box. All right, in reality, there's a limit to how many of these buttons you want to press. No, but you could do it. You could literally have 20 sets of contacts on these things. And they'd all get pressed every time you press that button. But again, this makes wiring royal pain in the rear end. All right. So what we've started doing is we come down and we now have our PLC. Talked about this, guys, a little bit last class. So you have your inputs. It's going to draw 4 of them, 4 outputs. So we have our inputs on the right, and we always start at 0. And you have your outputs on the right. And this isn't necessarily right and left. All right. If we take a look at this, and we look at this one, at the top, that's where our inputs are, and at the bottom, that's where our outputs are. All right. And again, if this was if we had more modules on the side here, where the Ethernet switch is, that would be your inputs. The next one would be your outputs. And the next one could be inputs again. The next one could be outlets, or it could be analog, or high-speed counters, or whatever combination of I/O that you need. You would just keep slapping them on, more and more modules on. I think this PLC can handle up to 8 modules for inputs and outputs. Or you could have communication modules there. So it's just never-ending game. But anyway, so what you would do nowadays is you would take this and you say, this is a syncing input, so we're looking for 24 volts coming in. So we would have our 24 volt line here, and you would just run off of this, and it would be overall, traditionally, 1 input per input. So we have 1 limit switch there, you have another one here, and a third one there. And then maybe you have a little push button going on down here. All right, and you just have 1 input, 1 actual sensor, button, limit switch, photo, whatever, per input on the PLC. Could we, in theory, put a second limit switch here? Any takers?
Yes.
Yeah, in theory you could. All right, that would be permanently wired in series. So So you have to think about that in your code, that like both limit switches would have to be true for whatever it is to be true in this code. But yeah, you could wire multiple in series. The downside of doing that is it makes troubleshooting harder. Because if you don't know that there's two freaking inputs, two limit switches on this, and you're out there pushing a limit switch going, which one is this? And you're like, it's not lighting anything up. The wiring must be screwed up. Now you're having a problem troubleshooting because you're thinking one sensor goes to one input, which is overall the standard. But yeah, you could do two in series. You could do two in parallel if you would want to. You could do something like that. That would be fine. That's an or statement, so one or the other. But again, ideally, one input per input on your PLC. Now, and then you have your output over here. In our case, we only have the one output. Now, as I was talking about with the push button earlier, if you were going to do one push button and have it on like 12 different rungs in the real world, you would have your one push button, and that would come down and it'd basically look like this. Where all of these would be different rungs. So you'd have, input, this would maybe be your start for your motor, this would be your start for the hydraulic pump, this would be the start for the, whatever, but they'd all be their own separate rung. And it makes, again, troubleshooting a real pain. In the PLC world, you would just call sensor input 3 multiple times, and everything is good. So it makes wiring a lot easier. Now, some may argue, and I can't blame you if you're going to be one of those people, that this wiring here, down at the bottom, is more complicated than the wiring up here, because here it's just one after the other, after the other, after the other. But down here, it's one that goes to an input, one that goes into an input, one that goes into an input. So you may actually have an extra 100 feet of wire now, because depending on where these sensors are in the machine, they could be like within 3 inches of each other or 4 inches. And they all go back to a PCL, which is across the room. So you have much longer wires. But when it comes to modifying things later and troubleshooting, having that PLC is going to be so much simpler. So in the long run, that's how our PLCs are going to get wired. Right? Now, this does take us to the next point here. We've talked about normally open and normally closed, right? So we've talked about how a reflective photosensor is, or a through beam is normally closed, and a reflective is actually normally closed, but the, what's the last one? Retroreflective, that would be normally open. All right. However, if you're gonna if you're gonna relay logic wire this, you're gonna wire it all hard together. You would have to maybe use relays to invert logic, because you're like, that sensor is normally closed. I need it to be normally open. Well, now you'd have to put that sensor to a relay and then use the relay contacts to then make it normally open. So you might have extra relays and things like that to invert your logic. And this is one thing that many students have a very hard time with. You have a normally open push button. So this would be a normally open. And you have a normally closed push button. All right. I think you guys can all handle that one. Right. Power, and this one stops when it hits the push button unless it's pressed, where power for this one flows through unless the push button is pressed. However, in PLC world, we can take whatever that sensor value is and invert it in an instant. All right. Because we have what's called a make sensor, which looks like this, and then you have a break sensor, which looks like that. All right, so the whole difference is that little line. And that little line drives many students insane. And the one thing that also many students think is, if I have a normally open sensor in the real world, I have to use a make. And if I have a normally closed sensor in the real world, I have to use a break. That couldn't be farther from the truth. You can have a normally open sensor in the real world wired to a normally closed break symbol in the software. Now, I call them make and break. I was watching some YouTube videos on the Big Bad Tech channel. It's a guy, I think in Ohio, who makes videos about PLCs and all those other fun things. And he's the one that started me on make and break. And the reason for it is, could you call this symbol normally open and this symbol normally closed? Yeah, you could, right? Because power for this one again stops, and the power for this one just flows right on through unless the symbols, the input's changed. But by going with make and break, trying to be consistent, that anytime I'm talking about software symbols, I'm saying make or break. And anywhere I talk about real world contacts, push buttons, limit switches, sensors, whatever, I am talking normally open, normally closed. So that way it separates the two. So I'm like, oh, that should be a break contact. Or is that sensor normally open or normally closed? That way it's just, anytime I talk about those things, it's one way or the other is really what it comes down to. So really, really kind of important in that aspect. So makes and breaks. They are wonderful and they suck. This is really what it comes down to. So I do like to point those out. And again, if you actually would look at the Siemens software for what they call it, I don't know what it is. I'll open the software up and we'll find out. I know, go ahead.
So when are we going to get to a complete, when are they going to get to a complete standard across the board?
Everyone thinks their standard's the best, so I don't think we're going to.
But, I mean, it does sound real, like I said, real world. Make it break, sounds pretty simple to understand, but then somebody else keeps it going the other way, you know what I mean?
Yep. Well, again, it's just, this is what our company calls it, and when all you deal with is Siemens, it doesn't matter as long as you're following that terminology. I've now been using make and break for 2 or 3 years, and I think it has helped out a lot when I'm talking with my students about these things. But if I go to industry and if I were using the term, oh, that's a make contact, they'd probably be like, what the hell are you smoking? That's normally open. It's yeah, it's a make contact. It's all about the language of who you're talking to. My mother always says that when we start talking in phrases that she doesn't understand, she knows our college paid off. And my brother will be like, yeah, the CBS of the QBT of the whatever. She's just like, yeah, I got no. Because he's learned all these acronyms around. It's that lovely game of, if you know the acronyms, you're perfectly fine. When you don't know the acronyms, then it becomes very difficult. So here we have the Siemens software, and if I hover over this, they go with, they actually call it a normally open contact. I know Alan Bradley calls it an examine if closed and an examine if open. I'm like, you gotta be kidding me. That's the terminology we're gonna use, examine if open and examine if closed. That just seems like way overkill to me. And I understand it's examine if. So is it true if it's closed or if it's true if it's open? But also, if I'm telling you guys that, it's backwards of probably what you think. An examine if closed is a normally open contact, and an examine if open if it's normally closed. So it's probably the opposite of the one that you think it is. So yeah, it's a fun old time is what it comes down to. Sure, let's go with that one. So anyway, programming is its own wonderful pain in the butt task. Right? I'm not going to ever deny that. I have a few people in here who have taken my PLCs class, and you're used to it at this point, which is great. And you guys will be perfectly fine as we go through these things. And some of you are still going to be like, you've got to be freaking kidding me. Because we are going to attempt to, we're going to do a little bit of programming at some point, probably next class. We'll get the PLCs out. We'll just do just a little bit of programming, just to kind of get you guys introduced to these things. Yes, some of you, you're going to have no problem doing this, but others are going to be cursing me left and right. It's going to be a grand old time. But anyway, so here we can kind of see some, that's my download manager. Here we can see some PLC code, and you can see I've got a make contact, which is again normally open, and I've got a break contact here, which is normally closed. And the real world switch here is normally open. So it's normally open, which lets power flow, and then as soon as this device rotates around and hits that limit switch, that keeps it from rotating more and basically running a stop into a wall. So that's why we we threw this up there. So, yeah. Now, the other wonderful thing you have in the world of PLCs is addressing. Right? And it's how do we reference the inputs? All right. If I pull back up my PLC over here, let me get the wrong button. I'll pull up my .cam. All right, let's give it a little focusy focus, and let's just zoom in some. Here we go. There you go. So you can see I have DIA and 0 through 7, and I have DIB 0 through 5. All right. And I appreciate them labeling them A and B. However, in the software, nowhere is there A and B. It's like, why did we go with A and B? Like, all right. In default, in the world of Siemens, it starts A is 0. So you have digital input 0.0 through 0.7. And then we have digital input 1.0 through 1.5.
You don't see it.
You don't see it. Thank you. Go to the right screen. There we go. All right, so you've got digital input 0 through 0 through 7, and input 1 through 10 through 15. Now, again, A would be 0, B would be 1. However, in software, you can change it. You can be like, nah, input A is now input 5. And it does go 5 and 6, and it's always one right after the other in this case. I don't know why you'd ever want to change it. Siemens gives you the option. I think it's silly, but I'm like, okay, I understand. It's there. You go to Alan Bradley and to the RS Logix 5000. Do I have that installed on here? No, I do not have it installed. It's like local, because you can have local or remote, depending on where your inputs are. The local would be attached to the PLC, remote would be all on the network. And then it's like local dot, 0 dot input dot, this is wrong, but anyway, dot data dot number. I'm like, holy crap. That is a lot to remember. All right. I mean, that's an RS Logix 5000. Go to 500 is a whole different game. It's just this never-ending game of things being different, which is the part that drives me abso-freaking-lutely batty in the long run. So the labeling of these is really annoying. And again, you will get used to this. You're going to be in whatever environment it is that you're in. That's mainly an Allen Bradley, mainly a Siemens. Those are the two biggest names in PLCs are Siemens and Allen Bradley. I was just talking to an ABB rep who is the robots that we have in here. And he said that Allen Bradley might be actually starting to lose some market share. Allen Bradley is mainly, I think, a US-based company, where Siemens is Europe. So Europe uses a lot of Siemens, where Allen Bradley is more US-based. It doesn't mean there's not Siemens PLCs here in the US. Obviously, I have a whole 12 of them in the closet back there, so we use them here. But then there's also, so these are the two major. And then you also have a company called Click. You have Mitsubishi, which I can't spell, but it's okay. You have, he said B&W, I think, or something like that this morning. So there's a lot of different brands out there is really what it comes down to. So it is something that you just kind of need to be aware of. So, and they all go to the different thing, which is also the pain bump. And their software looks different, and they call things different. I'm like, can we get a little bit of consistency? Just a little. Like, I don't want all the consistency. I understand that, but I need a little bit. And all their software is different. It's like, oh, the button for this one's here, and the button for that one's there, and they call it this, and it's like, jumping from PLC program to PLC program sucks. So, if I were you guys and you're ever like the ones in charge of picking PLCs for ordering equipment, when you're ordering it, say, I want this brand PLC, whatever one you have. Yeah, it's going to cost you an extra $2,000 or whatever because they have to buy a PLC, which is going to cost $1,000, and then they're going to have to program the PLC. So they actually have to rewrite the program that they already have, but in Allen Bradley to Siemens or whatever, it's going to be well worth your time for your technicians to have everything be the same. It also, in theory, will save you on licensing if you don't have to buy any more software. So that's big. But yeah, if you've ever worked in a shop where it's like, oh, this one uses Siemens and that uses Click and this uses an Allen Bradley, and the techs just hate it because they have to learn 3 different pieces of software to troubleshoot sometimes. So it's just not a fun thing. So if you can order equipment and be like, yeah, but I want it with Allen Bradley. Yeah, I don't care. It don't cost me more. That's fine. What's the more price? And that $2,000 will save you time in the long run, which will save you money. So I'd highly suggest that if you, again, have the opportunity. Many people don't have that opportunity. It's just for buying stuff. And the other benefit to having it all in one is you can monitor it all a lot easier. You all have one company. You could have one HMI that talks to every freaking PLC in the building that's on the network. So you could have one master control station, and this makes your life a lot easier. So that'd be my suggestion, but again, to each their own. So, but anyway, in the world of Siemens software, let's just do this. Let's add a new device. So here you can see we've got Siemens, we've got 1200, 1500, 300, 400. I've got no clue what the ET200 is. But you know, and then inside the 1200, you've got 1211s, you've got 1212, 14, 17, more 14s, 15s. The list just goes on and on. And some of them are just different enough. Like, oftentimes I have students and I'm like, you need the 1214C AC/DC relay BG40, which is this one, and they'll select the BG31. Yeah, you've got 3 variations of the AC/DC relay. I'm like, you gotta be kidding me. But let's see. So they're all slightly different as you pump. This one has 50 kilobytes of work memory. This one has 75. This one has 100. This one is expansion of 1.1 millisecond, 0.04 millisecond, 0.04 millisecond. This one has 2 pulse outputs. This one has 4 pulse outputs. They're all just slightly different. Like, I feel like it'd be easier for them just to make one model and just increase the price slightly and be done with it. Kind of go to the world of Tesla here, where it's like, okay, we're going to produce one model Tesla, and if you want heated seats, we'll enable it in software. If you don't want heated seats, they're still there, you just can't use them. Saves them money. They charge everybody a little bit more, and it just covers their bases anyway. But then if you want to add heated seats later, it's just a software update. You know, pay the fee, and you're done. You got your heated seats. So, little give and take on that aspect. But yeah, so look at like crazy different naming schemes, and you know these are the model numbers. 6ES72141BE30OXBO. You got me stinking kidding me. All the slight differences, and I think those are HEs, AIDS. Yeah, but they still HE40, BG40, AG40. I'm like, they're all still so stinking close. It's like, okay, we're gonna change one letter in these models, 2 letters maybe. But anyway, so you just need to be very careful. Oftentimes, if you select the wrong one in the software, you can say, change device and change it to this other one. And sometimes it works. Sometimes it's like, no, you can't select the device you want to select. And my students have written like, 10 or 15 lines of code. It's like, kind of have to start over. Got to add a new device, select the right one this time. Then most of the time you can manually copy your tags and your code over. It doesn't always work, but you can, at least that's a good place to start first. So, yeah. Highly suggest doing that one. So it's just this never-ending game with PLCs. But anyway, you can see some code here. No, of course, that's not going to work now. There we go. Can I draw? There we go. You can see some code. All right. And again, this is very simple code in the long run. I've seen programs with over 1,000 lines of code, and that's 1,000 lines strung up over like, I don't know, 10 or 15 different subroutines. And I'm guessing at the 1,000. I haven't gone through every subroutine and counted every line of code. I don't need to. I'm like 1,000 lines of code. Okay. All the PLCs have a specific amount of memory that you can load your program into. And while I've never hit a limit, I've heard stories of times where they've hit limits. It's like, yeah, we need to change PLCs or optimize our code to reduce the amount of memory being used because we don't have enough space to save the code to the PLC. I'm like, how big is that freaking code? How long does it take to run that code? Yeah. I mean, it's like I've never seen over like 2 milliseconds for my loop times. And that's normally like one time it was 2 milliseconds, probably like the initial run. And then after that, it's been back to 1 millisecond. How many lines of code is it? Like 1,000 lines. Is that a 10 millisecond loop time? Is that a 3 millisecond? Like, what is it? How many lines of code do we run per second here? That's just really impressive to me that they can run all that and still, have everything functioning. I'm always tempted to be like, okay, can we offload this to another PLC? That's going to increase cost, but it might definitely decrease your complexity of your code because you're only going to have 500 lines of code on this one and 500 lines on that one, or makes troubleshooting easier. You're going to jump through less hoops, types of thing. So it is a little bit of a give and take. There's never going to be a question, but definitely something to think about in the long run there. A lot of PLCs. We talked last class about analog and digital. All right. Let me clear that. Let's go back to this. All right. When we think about digital, or hopefully when you think about digital, we've got analog. You've got your chart here, and your temperature is constantly varying. So doing something like this. All right. Unluckily, analog and digital don't mix well. All right. If you ever hear like a real audio file, like a true audio file, they want their whole system to be analog. They want a record or a tape deck that has an analog value on it, and they want to be able to stream that through analog components to their speakers. They don't want to go analog to digital back to analog because when we were dealing with digital, you were dealing with pulses, like ons and offs. Now, you might be able to do like a pulse and then another pulse higher and another pulse higher and another pulse higher, which gives you 4 levels of analog. You have level 1, 2, 3, and 4. But it's still not true analog. It's still little sharp corners there. So the world of analog and digital truly do not mix well. All right. So what we have is we have ADCs and you have DACs. So ADC is your analog to digital converter. So what do you think a DAC is?
Analog.
Yep, inverted, digital analog converter. So an ADC would take this variable temperature sensor here and convert it into, say, an 8-bit number. So 1, 2, 3, 4, 5, 6, 7, 8. All right, and this goes back to the whole wonderful world of binary where these can all be zeros and ones. And when you add them up, you would have 256 different possible combinations there. So if your temperature sensor had a range of, say, 10 degrees from 90 to 100, actually, let's make it 25 degrees, so 90 to 115, you would have roughly 1 degree steps. So you'd be able to say whether it's at 90 or 91 or 92 or 93, whatever the case is. That's how many steps you'd have. Well, if you needed higher precision, say you need to go down to 0.5 degree, all right, you have 2 options. Option 1 is buy a different temperature sensor. So instead of a 25 degree range, it only has like a 12 degree range. So maybe you only have from 90 to 102. Now you have 90, 90.5, 91, 91.5. You have every 0.5 degree increment. So if the temperature sensor is reading 90.4, it's going to round it up to say 90.5. If it's reading 90.2, it's going to round it down to 90. So instead of having this beautiful curve here, you actually have a whole bunch of steps. Those steps should have a common width to them. So it's between those two. The sensor is going to tell you, hey, it's actually this value, but your digital computer can't deal with it. All right? And this is why audiophiles, or something people who really like analog, don't like a digital world, because you're losing information. You are actually losing information. It may be a small microscopic amount, but you are losing that information. Now, I told you one option was finding a temperature sensor with a smaller range. The other option is finding a better DAC or ADC. So instead of an 8-bit, you went to a 9-bit. That now gives you 512 different combinations. Or you go to a 10-bit, which gives you 1024. So you could do those types of options. Well, if the same 25-degree range, this gives you 0.5, this one gives you 0.25-degree accuracy. So that's how the PLC works. It's the only option it has. All right. So it has to take that, it converts into a binary, zeros and ones, which then the PLC can then convert from binary back to decimal and say, oh, that is 256 or 892 or whatever the case is. But all it knows is it's just in this range. Now you have to take that number and convert it to the temperature. Yeah, it's this lovely world we work with analog. So yeah, you're going to have this analog range here, and you're going to be like, okay, I have a number of 892. What the hell does that mean? Like, well, 892, we offset, we do times, 0.01 plus 90. And that 90 is because our lowest it will read is 90. So that's saying our offset up vertically is 90. And then we have times 892 by 0.01 because that's our step size. And then that would say, oh, you have a temperature reading of blah. So it's not just an analog world, not just a simple thing, which is why having those analog digital comparators, those analog comparators that we talked about last class, where, as I told you, you have a box with 2 dials on it, 3 outputs where it says it's low, it's acceptable, or it's high. Those are nice because it's just turn the dial a little bit and you're good to go. So I like those. And then the same thing happens with the DACs. It will pulse out, at a certain speed, but it's pulsing out, it's actually, sending these pulses, and it's okay, it's a voltage of 15 volts. That's all we can tell. So it's a lot of give and take when it comes to the world of analog. The other thing we do with an analog world when it comes to PLCs is comparators, which I have. Not going to work again. Let me get my pen back up. We have comparators, which we have right here, which, as you can see, these are both doing less thans, but they could be less than, they could be greater than, they could be equal, they could be not equal. This is my favorite. How would you guys say not equal with symbols on the keyboard? Right? The less than sign, that's on the keyboard. The greater than sign, that's on your keyboard. All right. Some places use exclamation mark and equals. That's saying not equals. All right. Siemens uses less than or greater than, which actually does make sense. Like you're like number 52. Is it less than 100 and greater than 200? It can't be both less than and greater than something. So it does actually make sense. It truly to me makes more sense than not the exclamation mark, except for I'm used to the exclamation mark programming things. So I would have preferred the exclamation mark, but they use less than and greater than back to back like that. So it's a little bit of give and take. You also have math operations, which I don't have in this code, but we pull some up. So you could do like an add block. All right, and oh really, man? Why are my shortcuts not working? Maybe it's bigger. And you can see the add has an in and an out, in one, in two, and an out. And my fun thing here is when you go to like a subtraction, in one, in two, and out. Which one, if I were to write that out, would it be in one minus in two, or is it in two minus in one? I guess the order does matter, right? With subtraction, there's a difference. So it's important to know which one it is. I believe it's the top one. Yeah, so to help solve that problem, I like the calculate block because then you can just come in here and actually write out your whole function, and it's just plus minus with parentheses, and it's actually a calculator, so it makes sense. And down here they tell you all the instructions. So you've got absolute, negative, exponent, fraction, linear sine, cosine, tangents, square root, round, cells, plus, minus, divide, all sorts of options there. So I like the calculate block when you can use it, but sometimes it's very confusing to use. I will tell you that right off the bat. It sometimes makes no sense when you're using it. So the world of analog is, in the long run, very, very hard in my opinion. So something just to kind of be aware of. But anyway, so PLCs. Any major questions on those so far? All we've done in the world of PLCs is we've taken we took this rung right here and we went from having it hardwired to wiring them up individually, so one input per input, or one sensor per input, I should call it. And then we write this in the code on the PLC. But instead of using these symbols, we would say it would look like this. That's the whole difference. All right? And it's lovely. I'm telling you, because I've had students wire up those boards before. I have boards back there with buttons on them and things. Maybe I'll make you guys do it for fun. My fun, not your fun. But I've had students wire them up, and this is something I did in my undergrad, which is why I created the boards here. And it's banana wire, so you just like jumper things back around. It's really nice, really convenient. But when I did it in my undergrad, all we had was red wires. So you're like, this is the program, right? You wrote something like this. That's the program. Great. And then it didn't work how you thought it was going to. And you're like, how do I modify this? And you're following wires from like one switch to another switch to another switch, and they're all wired together. And it just sucks. All completely sucks. No question in my mind about it. It's a pain in the rear end. So much so I've heard stories of people who work for the power company. They were doing some training, and they were looking at like substations. And the training substation was this beautifully wired wall with every wire had a different color, or the colors meant certain things. And the students were like, so teacher, like what happens when they're all the same color? And he's like, oh, it doesn't matter. And they're like, oh, it makes it a lot harder. Oh, it doesn't matter. During lunch, the students rewired the whole thing with one color wire. This teacher was cursing them the rest of the day. It makes a big difference having different color wires, or having things numbered correctly and stuff like that. So it is a big difference when the system is wired correctly. Just like it's a big difference when your stuff's in a program and you can literally just scroll through it. You can just be like, yep, that line or that line. If I had 20 of these lines and they were all wired, well, they're all going to be wired alike and they're all going to the same color wire. And oftentimes you're going to have this in a wiring cabinet. See if I can quick find that picture again. I found it yesterday. This one isn't bad, actually. Figure out what my search was that made it pop up. I don't know if I showed you guys this last class. Actually, that's my PLCs, robot people. Yeah, no, this one's actually pretty nicely done. If we actually were like to zoom in. But down here at the bottom is their PLC. And every one of these green squares is another output card. So these actually just come up here and connect. So that way, if they had to replace a module, they just unplug one big connector and plug a whole other connector back in. So makes life a little simple. Normally there's like edge connectors on there for the contacts that you can still unscrew, so you can take the whole thing off at once, but it's a bit more of a bigger mess that way. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 different I/O cards are on this. And I think most of them are 32 wires, 32 I/O. 13 times 30. That's what, like 300, 400, somewhere around there, I/O on this card, on this PLC. 400 I/O. Now, they did a very good job of this, but if you look at this, if you were to try to follow the wire from down here to somewhere, you can't. Because the first thing it does is it goes into this nice wire hider at the bottom, which keeps the wiring organized. And then that wiring may go up here to a fuse or to a place where it can connect two wires together, which then may go out to the machine, which may come back, which then may go out to the machine again. So you can't just be like, oh, let me just follow this wire along. You have to get the diagram out. You have to go, what does wire 13 connect to? Which, again, this one they did a very good job. If you look at all these wires, you can see that they all have little white tags on them, which are all numbered. So as long as their wiring diagrams are kept up to date, they can go, wire 13 should go out to the sensor. So they should be able to go from here out to the sensor, find wire 13 and go, all right, it's that sensor, and be done. Or that should go up to this fuse up here. Okay, so there's a fuse before it goes to the sensor. All right, so we need to follow that fuse. All right, oh, we come to the fuse. All right, that now goes to wire 12 or something like that. So it's just a royal pain in the butt when you have these giant wiring cabinets. And this is the wiring cabinet with all of the logic being done inside the PLC. Imagine what this cabinet would look like with, instead of having a PLC controlling it, having relays. And say there's 1,000 lines of code. If there's only 400 I/O, all right, let's say there's 200 of those are outputs. There's 1,000 lines of code. That means 800 lines of code don't have an output assigned to them, which means there'd be at least 800 relays added to this cabinet. Holy crap. I could not imagine troubleshooting that. That's really what it comes down to. Troubleshooting that does not sound fun at all to me. So it's just something that you got to keep in the back of your mind when you're playing with the wonderful world of PLCs. All right. So yeah, it definitely makes life easier because you can follow things, you can search for things. You can be like, where's input 36 used? And you can search for it, and it'll jump you from like round 1 to 50 to 300 to 301 to subroutine, whatever. It'll just jump you from point to point to point, which definitely makes your life a lot easier. So huge fan of that aspect of things. All right, so I showed you the Siemens software. Here is what Alan Bradley calls their connected components workbench, which is for that Micro 800 series. So if we come in here to what we need to do, ladder diagram. So let's see, I call it what I remember. A direct contact and examine if closed, or a reverse contact and examine if open. Back to my whole make break logic here. All right. So again, you can kind of see how the software is different. Let's drag it down. Now it makes you select your input. Don't have any, so that's fine. So yeah, it's the Wild West of when it comes to PLCs, of all the different versions of all the different software. So that's why I started making breaks. Other teachers doing it, and I'm like, that makes perfect sense. I'm going to jump on the bandwagon and go make and break. And that way, no matter what the software calls it, it's still a make or break. So I don't care if I'm using Alan Bradley, I don't care if I'm using Siemens. If I tell you a make contact, you know that it's that contact, a normally open contact. So, all right, so that is my brief introduction to PLCs. We're not going to really dive down a rabbit hole. So there is a whole other class in PLCs, INT 102. All right. If you haven't taken that yet, I highly suggest taking that next semester if you need to take it. It is a fall-only course. All right. For those who are in the ADM program, there's also an ELE 203 PLC course, which is in a springtime course. So if you have to take that one, I'd suggest taking it right after you take INT 102. Yeah, it's INT and ELE. I don't know why they're different. I just had to convince Ed and Juan to submit the paperwork to move them to be ADM or INT. Just pick one category. I don't care which. Just pick one. Make my life easier. Call it PLC for all I care. But yeah, it'd be really nice if we could just make them all category and be done with it. Same with robotics. That's ELE 140. That also should probably be ADM. So, but yeah, so my rough introduction. Next class, we're either going to use the Connected Commodes Workbench software. Probably not, 'cause I don't think I have it on all those laptops. So we'll get out the Siemens PLCs, we'll open up TIA Portal, and I'll have you guys write a few simple programs. Maybe make a conveyor belt move for fun. Do a little wiring real quick, just to give you guys some experience and love for the world of PLC wiring. Yeah, you're all smiling. You're like, this is gonna be a grand old time. Those have already done it. You're like, it's gonna be easy. I think PLC should be a prereq for this class, but that's a whole different game. So, all right, gentlemen, that is all I've got for today. Have a wonderful time, and I'll see you all on Thursday.